Hello and welcome to today's lecture. Today we will look into some of the most important natural constructions on schemes that will allow us to use the full theory to study these schemes further, and also we will look at the relative point of view where schemes are viewed over other schemes, and this will help us better relate the scheme point of view to the variety point of view. So recall that an affine scheme is a locally ringed space of the form spec R for some unital commutative ring R. And the scheme without the adjective affine is a locally ringed space admitting an open cover by affine schemes. This means that an affine scheme, or just a scheme, is a topological space with a structure sheaf. And locally ringed means that the stalks of this structure sheaf, this sheaf of rings, should be local rings. But you can also look at a scheme as a representable functor. So in the affine case, this means that whenever you see the notation spec R, you can either think of this in the way we have defined this as the prime ideals together with the structure sheaf, or you can view this as the representable functor home in the category of rings from R to blank. And depending on your preferred point of view, these two will be useful in different ways. Also, depending on the context, these two are more or less useful. But they give the same information and they both give you the information about the scheme. The important point, though, is that what you should not do is you should not look at the underlying set of the scheme and just that. That is a weak concept because different schemes may have homeomorphic spaces. So, for example, spec K for any field K is just consisting of one point. So that is already bad, but also spec of the ring of dual numbers only consists of one point. So you cannot only look at the underlying space, you actually need the algebra. If you prefer the functorial point of view, this is in a sense the reason why we actually need a whole functor, hom R blank, rather than hom R to some fixed ring. But this also has a consequence when we want to define such things as subschemes, embeddings, intersections, and unions. If we do this purely set theoretically, we have a high risk of failure. So we need to be vigilant and define these things appropriately. And this is what we will keep in mind throughout this lecture. The first thing that we will look at are open subschemes. And here we can still be a bit relaxed. So if X is a scheme, then an open subscheme of X is simply an open subset U of X endowed with a structure sheaf that is the restriction of the structure sheaf of X to U. This is a well-defined scheme because all the sections of OU are already sections of OX. So the fact that the space is locally ringed, for example, is given. And the usual inclusion gives us a morphism of schemes from U to X. And so the slogan is that open subspaces naturally inherit a scheme structure from the large scheme X. But for closed subschemes, we need to be careful. So let's start by defining closed subschemes in the affine setting, namely by defining affine subschemes. So let's stop and think about what this meant when we dealt with varieties rather than schemes. So if X was a variety, then we defined a closed subvariety, an affine subvariety, or an algebraic set included in X. Well, it was a set, But also recall that the coordinate ring of y was, or could be identified with, the coordinate ring of x modulo some ideal that we probably denoted in this fashion. And another way to say this is that y was the maximum spectrum of the ring R, if x is the maximum spectrum of R, modulo some ideal j. And now, as we went from varieties to schemes by removing the m, this is exactly what we will do. More precisely, we'll define an affine subscheme of an affine scheme x as an affine scheme y in its own right, together with a morphism from y to x, such that its pullback morphism from R to S is surjective. So let's unpack this. Remember that a morphism of schemes consists of the additional datum of I star in the reverse directions from OX to OY. In particular, this induces a ring homomorphism from OX of X to OY of Y. But this is just R and this is just S. And so this morphism is the one we require to be surjective. This is, by the isomorphism theorems for rings, equivalent to the fact that S is isomorphic to R mod some ideal J. So the slogan is that affine subschemes correspond to quotient rings. And indeed, we get a correspondence even with the collection of ideals in R, namely the assignment that to an ideal J gives us the spectrum of R mod J, defines a bijection between ideals in R and affine subschemes of X, X being spec R. And this is exactly as we would expect. So let's look at an example. If R is the scheme or the ring of polynomials in one variable over, say, an algebraically closed field K, so that spec R is the scheme associated to the affine line. And if we then take J1 as the ideal generated by T, then R mod J1, this is the point, well, R mod J1 is isomorphic to K. So this is the usual point in the sense of varieties, or the schema, the spec of this ring will be the scheme associated to the variety whose underlying set is 1 point. But we can also take in the same ring the ideal generated by T squared. And then R mod this ideal will be the ring of dual numbers, which has the same underlying set, but is different algebraically. It is this point that is, in some sense, extended infinitesimally in one direction. Now, let us look at intersections and unions of such affine subschemes. So if we have X equals spec R and two ideals, J and J prime, then the union is rather straightforward to define. Namely, the union of spec Rj and spec Rj prime is the affine subscheme where we mod out the intersection of these ideals. This is reasonable by the Nullstellensatz, even the one for schemes, because it tells us that such intersections of ideals corresponds to unions of sets whose vanishing ideals these ideals are. The intersection is a bit more intricate. We define it as the affine subscheme where we mod out the sum of the two ideals. This is intricate because remember when we dealt with varieties, we modded out by the radical of the sum, not just the sum itself. Rather, the vanishing ideal of the intersection was the radical of the sum of the two ideals. And this difference precisely relates to the difference of schemes having the same underlying set. So for example, if we look now at the affine scheme corresponding to the plane, the affine plane, over some algebraically closed field, and we take as J the ideal generated by T, and as J prime the ideal generated by T minus S squared. So in pictures, this is something like this. It should be the intersection of the parabola and the affine line that we get if we intersect the corresponding subschemes. And if we do this, then indeed R mod J plus J prime, this will be isomorphic to Ks mod S squared. Again, this ring of dual numbers. And so this means that we have a double point here somehow. Namely, we have a point that is essentially extended infinitesimally in one direction. And the topologists in the audience will recognize this as some sort of non-transversal intersection. And indeed, the point is that the tangent spaces, both intuitively and actually, align in this point. So we get some information both on the level of points and on the level of tangent spaces. What would have happened if we had taken the radical before quotienting? Well, then we would just be modding out with S, not S squared, and we would get the normal point. So having defined closed subschemes in the affine setting and called them affine subschemes, let us do this in the general setting. So we take any scheme X and we want to define what it means for a scheme to be a closed subscheme of X. The idea is, of course, to have an object that is locally an affine subscheme. More precisely, a closed subscheme of X is a scheme Y with a morphism from Y to X, satisfying the following property. So for any affine open set U in X, the induced map from the pre-image of U in Y to U should be an affine subscheme. So a couple of remarks. The first remark is that it's enough to check this not for every affine open set, but only for sets in a fixed open cover by affine sets of X. Also, this definition suggests that closed subschemes should correspond to sheaves of ideals. So these local constructions for affine open subsets, these are affine subschemes. So they are defined by one ideal for each open set. So what we seem to be having is some collection of ideals, one for each open set, namely in some sense a sheaf of ideals. And we will get to that further on in the course, and it will turn out that this is exactly the situation that we have. Now, one thing that should be mentioned in this context is that schemes can be glued. This should be expected both because a scheme was defined precisely as a locally ringed space with an open cover by affine schemes. So in a sense, we had implicitly the gluing of these affine schemes, but also for varieties, we managed to glue varieties into other varieties. And so this slide is almost exactly a copy of the slide for varieties, mutatis mutandis. The only difference is that we allow ourselves to glue infinitely many schemes. So given schemes xi with open sets uij and isomorphisms between them, satisfying the reasonable compatibility properties, we again can define the set where we, in the disjoint union of these xi's, identify points via these isomorphisms. This gives us natural maps from the xi into this x. We topologize x by declaring a set open if it is open in the quotient topology. And we make this into a locally ringed space by defining the structure sheaf as the unique sheaf of rings whose restrictions to the ui's are isomorphic to the structure sheaves of the ui's via isomorphisms compatible with these patchings fij. And here ui is the set xi or its image under this map. So it is these open sets that will make up our x. All of this looks way more technical than it should be. The idea is simply that you glue together schemes along isomorphisms and define all the structures you need in the only possible way, and it works. The important example is if you have a set that has an open cover by affine schemes, then these isomorphisms are simply the identities on the intersections. So you get everything naturally and it becomes less technical. This gluing will help us to associate schemes to pre-varieties. So we have previously associated schemes to affine varieties, and now we can glue them together to get schemes associated to pre-varieties. Namely, given a pre-variety X over an algebraically closed field, we denote by X SCH the set of all closed irreducible subsets of X. It is reasonable as a generalization of the set of all prime ideals because prime ideals correspond precisely to irreducible closed subsets. So now we have a set, and since X is a pre-variety, it has a cover by affine varieties ui. To each affine variety, we have the associated affine scheme, and we glue together these affine schemes, and these precisely cover this set X SCH, and so this gives us a scheme structure on this scheme, on this set. We call this the scheme associated to X, and it satisfies some natural properties. The first is that the open subsets of X SCH are exactly the same as those of X, and the structure sheaves have the same sections. This is simply because in both cases the open sets are built up from these principal open sets. And here you should understand the word R carefully, because in one situation you are only looking at the closed points, and in the other situation you're looking at all the points in these sets. Moreover, any morphism of pre-varieties naturally induces a morphism of schemes. And this is because morphisms of pre-varieties come with this pullback morphism that gives us exactly what we need. So this is our first step towards associating two varieties schemes and viewing pre-varieties and varieties as schemes. And we will get back to this later in the next part of the lecture, when we have more tools to deal with schemes and a more adequate language to look at schemes over a base, such as a base field.